All right, so now that we've introduced anti-differentiation and the idea of an indefinite integral, so integral and antiderivative kind of mean the same thing. So now that we've got that and we've kind of approached it more intuitively, now let's look at properties of integration and basic integration rules. So here's a handout that I will put on D2L for you. You've seen the left side before. This left side has been available to you since the beginning of Chapter 3. The right side is basically the parallel rules for integrals. So let's see what we've got. Over here, and I'm going to compare derivative rules, integral rules. So here, the derivative of a constant multiple is the constant multiple of the derivative. That's the constant multiple rule. A very similar rule exists for integration, right? The integral of a constant multiple of a function f of x is the constant multiple of the integral of that function. So constant multiples just stick around. You can multiply that constant multiple by the antiderivative, and you get the antiderivative of the original function. Same kind of idea with adding and subtracting. Differentiation, distributes in a sense over adding and subtracting, and so does integration. So the integral of a sum is the sum of the integrals, and with differences as well. By the way, you'll notice number 3 and 4 here are missing. 3 and 4 on the derivative side are the power rule and the quotient rule. Turns out taking integrals of products and quotients is actually much more complicated. So much so that we're actually not even going to get to it this semester. We're going to only get partway through Chapter 5, and then you're going to pick up with the more challenging, the more complicated integration rules. You're going to do those in the beginning of Calc 2. So that's called integration by parts. It's basically like the sort of integral equivalent of the product rule, and we're not going to get there. So for now, if you run into an integral of a product, you're going to have to find some clever way around it, or perhaps we won't be able to do it this semester. Okay. 5 here, we've got basically the integral equivalent of the chain rule. This is called integration by substitution, and that we're going to learn. That'll be one of the last things we learn this semester. Let's look though at 6, 7, and 8, which are I think and 9 too. These are some of the really basic ones. Okay. The derivative of a constant is 0, right? So therefore the integral of 0 is a constant. Okay. That is pretty straightforward. Okay, we've got this idea, derivative versus integral. They're kind of acting like inverse functions. Okay, input constant, output 0. Over here it's input 0 and output constant. So derivative and integral are in many ways basically inverses of each other. Okay. The derivative of x is 1, right? That's a very basic rule for differentiation. And the equivalent basic rule for integration is that the integral of 1 is x plus a constant. So we've got that. And then the number 8 here is our inverse power rule. Remember the power rule where you bring the power down and then you subtract 1 from it? So the derivative of x to the n is n times x to the n minus 1, right? We need to reverse those two steps, but in reverse order. So we're going to undo those steps in the reverse order, which means the integral of x to the n, the first thing you're going to do is raise the power up by 1, so we get x to the n plus 1, and then you're going to divide by that number instead of multiplying by it. And then of course you would add plus c. Now this means we're dividing by n plus 1. That means this is going to work as long as n is not equal to negative 1. Okay, if n is equal to negative 1, then you're in trouble because you can't divide by 0, right? If n is negative 1, then negative 1 plus 1 would be 0, right? So that's important. What happens if n is negative 1? Well, then if n is negative 1, then x to the n would be 1 over x, and that shows up down here. This is the n equals negative 1 situation. What is the antiderivative of 1 over x? Well, it's the natural log of x, of course. Don't you remember that the derivative of natural log of x is 1 over x, right? That's over here, number 11 on the derivative side. The derivative of ln x is 1 over x. So that's what's going on in here as well. Now I know you're seeing the absolute value in there, and I will explain that absolute value to you later on when we get a chance. But let's hold off on that for now. The only other one I want to point out here is this one, number 9. We already talked about this. The derivative of e to the x is itself, so the antiderivative of e to the x is also itself. And it might be worth just looking through these trig ones down here, these trigonometric ones, 13 through 18. These are just the exact reverse, the exact inverse of all the derivative rules. So those are pretty familiar already. Just remember the differentiation rules, flip them around, and you get the integration rules. So we'll discuss more of these later on. Okay, there's some inverse trig ones down here as well. But if you look over this yourself, I think that you'll start to see patterns. You'll start to see that everything over on the right side is just like an inverse of what's on the left side. It all makes total sense, given the idea of anti-differentiation is like reversing a derivative. So we're going to use some of these rules to do an example. Okay, this is an example we already did, but I want to show you how the rules are applied to like rigorously prove an integral or an antiderivative. So we've already found the antiderivative of 6x squared minus 2x plus 5 in the last video. But let's do it again using integration rules. So first, since this is a polynomial and it's got 3 terms, it's a sum or difference in some cases, right? So what we can do here is distribute the integration over that sum and difference. This uses the sum and difference rules with the plus and the minus. So first we'll have the integral of 6x squared dx, and then we'll have minus the integral of 2x dx, and plus the integral of 5 dx. So the next thing to do is to apply the constant multiple rule. So here we have a constant multiple of 6. We can pull that outside of the integral, like that. So it was the integral of 6x squared. That's going to be 6 times the integral of x squared. That's pulling out the constant multiple. Same thing here. We can pull out this 2. There we go, in the second term. And then in the third term, you can actually pull the 5 out. What happens if you pull out the 5? Well, 5 was all that was there, right? So it's just like factoring 5 out of a term which is just 5. What do you get if you factor out everything? You get 1, right? 1. And in some ways, this is literally factoring out, okay? This integral sign, we're going to learn later how this integral sign represents an infinite sum, and you can factor out a constant multiple from a sum, right? And so in a sense, we are literally factoring, and that is why the constant multiple rule here is justified in some sense by just like the idea of factoring out a constant from a bunch of terms that have that constant in common, okay? So there we go. We pulled out the constant multiples. Now we can use some of the basic rules here. I'm just going to remind you what they are. Here is the inverse power rule here, number 8. So we're going to increase the power by 1 and divide by that number, and then throw a plus c on the end. So for this part here, we will get x to the power 3, okay, increasing the power by 1, and then divide by 3. So we have 6 times x cubed over 3. And now we have a plus c. Now I'm going to call this c1, okay? Because when I do this antiderivative here, I get a plus constant. Now we're going to get 3 of them. So they're going to be c1, c2, and c3. Heads up, you're not actually going to have to do this when you are... So I'm going to explain why it is you don't actually have to do this. Initially, it looks like we should, right? Because here we have an integral, so when we evaluate it, when we do this integral, we should put a plus c on the end. But it turns out we don't really need to do that, but I'll explain why at the end of this example. All right, so the next one, the integral of x, well, we learned that is going to be, we should increase the power by 1. Currently it's 1, right? So we're going to increase it up to x squared, right? And then divide by that number, divide by whatever power we got, so dividing by 2 in this case, with plus c2. And then the last one, plus 5 times what? Well, what's the antiderivative of 1? It's x. That's one of our basic rules. You can also think of this as x to the power 0. If this is x to the power 0, then you increase it from 0 up to 1, and then divide by 1. And you get the same answer. But then let's throw a plus c3 on the end. So there's our antiderivative. Now let's simplify this a little bit. We'll distribute here. Distribute this multiplication all the way. For each of these, we're going to distribute. So here's 6 times 1/3 is 2x cubed, plus 6c1. Now, minus 2 times 1/2, the 2's are going to cancel. So this is just going to be minus x squared. But then we'll have minus 2c2. And then over here, when distributing, we'll have plus 5x and then plus 5c3. All right, now we have three constant terms, right? We have this plus 6c1, minus 2c2, and plus 5c3. Let's combine those all together into one constant. Combine. Now, here's an idea. Wrap your head around this. If c1, c2, and c3 were all arbitrary constants, then if we combine multiples of those arbitrary constants, then the result, isn't that also just an arbitrary constant? Let me say that a different way. If c1, c2, and c3 could be any constants, any number, any real number, then if you combine multiples of those things, couldn't you still get any real number as a result? Like if the inputs could be anything, the output could be anything. This is true. So what it turns out is you can ignore the c1, c2, and c3. We could have just not done that. Or you could have just not done that at all. And instead put a single plus c on the end, which represents just one single arbitrary constant for the entire antiderivative. So what we're going to get here is we're going to pull out all the parts that are not constant. So there's all the non-constant parts. There's that part, there's that part, and there's that part. So there's those three. And then just plus c. That's it. Okay, and that is the answer we got in the last video by just doing it more intuitively. So there's an example of how to apply the rules. You don't have to do the plus constants individually. You can just apply the rules more, generally. Like you could have just had these parts here, like just the x cubed over 3 and the x squared over 2 and the x, and then put your plus c on the end at, when you're done. Okay, but otherwise, I do want you to be able to apply integration rules like this step by step, in a way that kind of rigorously leads us to the antiderivative.